But really exciting time to be in Bitcoin right now. There's a lot of stuff that's going to come out soon. So that's a whole other set of talks.
Out of curiosity, when you say Bitcoin, do you mean Bitcoin specifically, or do you mean cryptocurrency?
There's always something happening in cryptocurrency, but in particular, really excited about Bitcoin right now. Cool. We good?
We're good.
Okay, so folks who have seen some crypto stuff before or have been following Bitcoin will know Alice and Bob. Whenever we explain some sort of interaction with cryptography, there's usually two players, Alice and Bob. So what I want to explain here is why, first of all, what are digital signatures? That's what this talk is about. Digital signatures are a way of proving, when you send a message, that the person who's sending it is really who they say they are. So an example is where you would actually use signatures imagine Alice was sending an invoice to Bob saying, hey, you got to pay your rent. So Bob will get this message. He'll see that he needs to pay the bank account 79BE667E. He'll get it, he'll pay his account, like everything's good. We don't need signatures in the scenario where Alice and Bob have a clear communication line between each other that can't be tampered with. And that works fine when we're like right next to each other, exchanging, talking. But on the internet, you can have people halfway across the world who are sending information between networks that are untrusted, and people in the middle of those networks can tamper with the messages. So an example of that is another character, Mallory, comes in, intercepts the message, replaces it with her own message. This own message says, send your rent payment to Mallory's account. And Bob is none the wiser. He thinks he's speaking with Alice. So the way we solve this in meat space world is we write handwritten signatures. You know, when you sign your check. And that works because for the most part, humans trust each other, which is awesome. But that doesn't happen all the time. And it's better to not have to rely on that because, well, it's not always true. And it may allow you to build things that wouldn't be true if you had to trust someone. So what we use in the internet world, where there's billions of people online who don't trust each other, don't know each other, are digital signatures. And a digital signature is just a collection of bits, a blob of information, which someone can use to validate, oh, Alice actually sent me this message. It wasn't Mallory. Or kind of similarly, a receiver can say, oh, the message I'm receiving is indeed the one that Alice wanted to send. Because that's what happened with Bob before. He didn't know that the message he was getting was actually from Mallory instead of Alice. So the way we're going to do this, the way these work, are something called, or they use something called public-private key cryptography. So the idea here is that someone, Alice, generates two keys, a public key, which she can give to everyone, and a private key, which she only keeps for herself. And these keys are just really large numbers, amazingly large numbers. I'll show you some examples of how large. But with these two keys, one sending the public key to Bob, and Alice protecting, only she knowing the private key, you can take that private key, perform this process where you take the private key and the message, and you can create this signature. And so now Alice, when she sends her invoice over to Bob, will send the message. Bob has the public key, because everyone has the public key. Alice just distributed it, sent it out via email, whatever way is easiest, and the signature. And Bob can use this digital signature algorithm to validate the signature. Okay, so even if Mallory comes in and replaces it with a different message, it's okay because Bob can go, hey, Alice didn't sign this message. This message which is telling me to send to some bank account is invalid. And so we can just discard it and not send his rent to some random person on the internet.
Is that best practice then to verify any PGP message you get?
Yes. Yeah, so there's Chrome plugins or browser plugins you can get that will automatically do that for you when you get an email that has a PGP signature. You can do it manually, just taking it from, usually it's email, but taking it from your email, copying it onto your computer and running a program. But yeah, that is definitely best practice. Yeah. Then it's just sort of like, we have a name for that. It's called security theater. It's when you pretend and act doing actual good cryptography practices, but in reality you don't.
Right.
Yeah. So I'll be honest, I've done that as well. I get these messages and the message just isn't that high value. You know, it's like someone complaining about a bug. And I'm like,
and so I'm assuming it's best practice to sign it?
Yeah.
Because, well, you have to encrypt it first, right?
No, encrypting is different.
Oh, okay.
You can encrypt it, but they're really separate things, even though they use the sort of same underlying mathematics to do it.
Right. Okay.
It's still public-private key cryptography, but no, you can just send a signature, so not encrypted. Anyone can see it.
Right.
Yeah.
About the Chrome extension, it's not really best practice because by itself to have an extension or plugin in Chrome, it's compromising the security. Because if extension fucked, you wouldn't understand what you compromise your password and stuff like this before you get fucked. So try to avoid using those plugins, extensions, whatever, changing the default settings of a Chrome while you're dealing with like pretty much any keys, especially like passwords, like whatever.
Yeah, and the larger point is that like you will learn that everything is broken. It's amazing this whole system works at all, like the internet works at all, because there's malware, there's attackers, there's everything. But if you really want to be really secure, you really have to do a lot of work to make it work. So there's always this balance, you know, like sadly it's often usability versus security.
Just one example, like I had an extension of Chrome which tracked my time, so I can see how much time did I waste in the social networks. And one day it just wasn't active and I check in the settings and it says it contains malware. So people who develop those Chrome extensions sometimes do not pay that much attention to security, and if they got compromised access to the plugin, potential attacker might just update this Chrome extension with keylogger, whatever is possible. For example, Grammarly, very popular extension which helps you to write English correctly, has obviously access to all this data you type. It's how it's checking because it's checked on a server, not locally. So
that's why I think like really clearly defined and documented modular permissions are important, and I like that that's at least the direction that Android's gone in to some degree, is like, okay, the user now has to check off on each new permission being accessed by something as it is, rather than, oh, read our terms and conditions as you download our app. That's not happening. But it's like there were the whole, I see this as a parallel to like the scandals of like the flashlight app that everyone suddenly noticed was like asking for complete admin permissions to people's phones, and it just went unnoticed for, you know, with hundreds of thousands of users. Like it is something that it is a pain in the ass to stay on top of, and but it's a community collaborative effort to call that shit out.
I mean, you get email applications that you can bundle signature checking into. So
yeah, open PGP.
I'm finally back on Thunderbird after abandoning years ago, and I've gone back to Thunderbird and Enigmail. So that's about the only combination that works out of the box for working with signatures.
Yeah, Mac Mail I think also works. I have someone at work who uses it. Yeah. So okay, so that's the reason for signatures. Please ask questions if it's not clear. The purpose of signatures is to validate the person who's sending me a message is in fact the person I think it is. Okay, and we do that through public-private keys. We identify someone with a public key. They sign a message with their private key, and then anyone can use that public key to verify. Yep, this is indeed Alice. Okay, so the next question is, how would we build one of these systems? And I'm going to show you elliptic curve cryptography, but there are other ways of doing this. If you've heard of an algorithm called RSA, that's actually older than elliptic curves and more prevalent. But the feature that these all share is that they make use of hard problems in math. That hard in the sense of it takes a long, long time of running a computer, running the process, running the algorithm in order to find the solution. Okay, and we take advantage of these hard problems because we want a signature that is really, really hard to forge. A signature that's really difficult for Mallory to come in, create a fake one, where Bob goes and takes the fake signature and goes, oh yeah, this is valid. That would be a horrible system if someone was able to do that. So we need to make that very hard. Kind of conversely, we need to make it easy to generate one of these signatures. You know, it's really, as like a non-digital explanation, it's really easy to, for instance, ID a world-class climber who goes and climbs up a mountain in South America and then leaves some sort of identifying piece of information up on the mountain. That's really hard to do, and no one would be able to verify it. So we need something that is easy to verify, easy to generate for someone who holds the private key, but very hard to forge. Okay? So I just want to make a distinction between these easy and hard problems. Easy problems just mean they take a long, long time for a computer to solve them. Okay, so like x plus y equals 2, super easy. This massive mathematical expression, also super easy. A computer can find the solution to this equation in milliseconds. But a hard problem, and the one that elliptic curve digital signature algorithm uses, is called the discrete logarithm problem. Okay, so the idea here is it's a pretty compact equation, but it is very difficult to find the solution. The problem is, given you know what these values are, n, g, and h, try to find what x is. So we're taking some number g, and I'll go more into depth of this. I just want to show you that this discrete logarithm problem is the fundamental problem we're going to use to make a secure signature algorithm. When you take g, raise it to some power x, and then take the mod of it n, we'll go into this, you get h, and can someone who didn't know x solve for x? Okay? Contrast it with this, where if I tell you y is equal to 3, anyone can solve for x. It's just 1 plus 2 equals 3. But here, if you only know g, n, and h, x is going to take longer than the existence of the universe to find the solution for. Very hard. And the reason they're hard is that we use gigantic numbers to plug into these problems. So going back to the public-private key cryptography, when we create these public and private keys, they're just long numbers, huge numbers. So a common size of an EC key, of an elliptic curve key, is 256 bits. So 256 zeros and ones. If you convert that into decimal, it's 1 followed by 77 zeros. And just, you can look here for some examples of how large this number is. If you had all the computers working for all the time in like unfathomably fast, it would not even come close to how large these numbers are. And the size of these keys, of these numbers, is directly proportional to how secure the algorithm is. And here's the craziest thing for me, is like, so there's this discrete logarithm problem which I just showed you, and the whole system rests on it being hard to solve. Hard and easy to generate a signature, hard to forge one. But we have no proof that it's actually hard. We've been trying for about 30 to 40 years to create an algorithm which can solve this fast, what's called polynomial time. It just means basically a computer could solve it in a reasonable amount of time. We haven't been able to figure it out. So if you could solve the discrete logarithm problem, you would instantly be worth trillions of dollars. You could go and alter any of the bank account software interactions that take place. you could go and disrupt communications between world leaders. You could do many things, and it all rests on this belief, this fact which we haven't even proven. So that's wild to me. It's like everyone's kind of, there's this lie and no one acknowledges it, no one can find it. Okay, so let's take a break. Any questions on what I've said so far? I'm trying to explain this idea of public-private key cryptography, and then we're going to go into elliptic curves and talk about how we can use elliptic curves to create, along with the DLP problem, to create a signature algorithm. Yeah?
Well, comment about cost $1 trillion, it might be not really true, because asymmetric keys is only like they use this hard problem of reverse algorithm.
No, symmetric keys use something
asymmetric.
Totally. Oh, asymmetric. Okay.
Yes, so if you're even able to break asymmetric key, you still have quite a lot of chunk of cryptography which is resistible for this like factorization problem. So economy is not fucked, basically. It just takes time to improve for different algorithms, which is, let's say, quantum computer resistant,
True.
But we do not use them because it just takes bigger overhead to calculate it. It's basically slower, but we already have pretty much all math necessary to prevent what kind of attacks.
That's
so
true.
it's just not widely used because right now is acceptable, but quantum computer is not a real thing yet.
The
But
problem is that
we do not fact, basically.
updating that will be a nightmare.
It's my
Like,
materials.
there's 20, 30-year-old software out there which is running our cars and our trains and our water systems that you have to go and totally replace.
Yep.
So it would be very bad. But yeah, so I didn't talk about it, but there is actually a solution. I kind of lied. There is actually a solution to the discrete logarithm problem that can be solved in polynomial time, so fast. But it involves quantum computers, and I cannot explain it to you. It's so weird and different and fascinating, but it involves using quantum states, so like atoms or photons, in order to actually perform computation. And using that, you can factor integers very quickly, or you can solve discrete logarithm problems very quickly. And they're building quantum computers right now. Google's working on it. The NSA is certainly working on it, but they're not there yet.
You do get recommendations for quantum proof encryption, right? There's some algorithms. So I think, is it NIST or someone changed their recommendations on what algorithms to use?
Yes, yeah.
To make them harder for quantum computers to crack.
NIST sent something out last year basically saying, like, prepare thyself for the coming post-quantum revolution. They also said not to use phones for 2FA, just random blurb. Don't use SMS for two-factor authentication. You should use something like Google Authenticator, or you can use one of these guys, a hardware key.
Yeah.
So we can talk about that after.
Key signing party.
Well, about SMS, it actually makes sense because it's relatively easy to get access for everyone's number.
Yeah.
I might speak after each lecture how it's possible to do it relatively cheap.
So it's amazing it all works. It just seems to keep coming back to that for me. Okay, so let's talk about elliptic curves. Let's talk about elliptic curves and the math behind them, and then we'll talk about how we can use them to create signatures. So what is an elliptic curve? This is one example of one. This pimply-looking curve is represented by that equation right over there. And some things you'll notice about it, it's symmetric about the x-axis. So it's like mirrored on either side. Humans have known about this for over 2,000 years. They were originally used to solve these things called Diophantine equations, which are polynomials, like you saw in high school, with integer solutions, and just trying to find interesting characteristics about integer solutions to polynomial equations. And we can define a mathematical system on these elliptic curves. Okay, so what do I mean by system? I mean we can agree on what an element in the system is. It's going to be a point on the curve. We can agree what it means to add 2 points, and we can agree on what it means to multiply 2 points. So we're all familiar with addition and multiplication. We're just abstracting this away, and I guess you can think of it as looking at it in a different way, or being more liberal, more abstract with how we define these operations. And these operations are going to let us build our public and private keys. So I will not subject you to this. This is a bunch of algebra which explains how you actually do the addition and multiplication. But the way it's first defined, and the better way to look at it, is through pictures and through graphs. So that's what we're going to do. So, okay, so what I want to do here is I want to show some characteristics of the system, of the mathematical system. We're going to use that system to create signatures. But first we need to understand the system. So one part is addition. How do you add 2 points on the curve? Okay, so the way we're going to do that is we're going to say if you have a point P, which is here, and if you have a point Q, can you see that fine? Which is here. The way we define addition is you draw a line between them, and you find where it intersects on the curve. And we're pretty much always guaranteed to get an intersection because this is a what's called a cubic equation. It has 3 roots. It will have 3 intercept points. And then we take the opposite point around the x-axis. Okay, so P plus Q is equal to negative R. There. Okay? You draw a line. You find where it intersects. That's not those 2 points. You flip it about the x-axis. So that's addition. Okay? We're free to do whatever we want, as long as the system has coherency, as long as it is internally consistent.
But it's not literally addition, like the x1 and x2 added together does not give you the x of R.
Correct, yeah. It's kind of like...
No, it's literally addition in a group of a prime number, but it's like we just define the sort of a group of numbers and put an operation which we call addition, and it has pretty much all features of add operation. So you have a transition, you have association. So it's just more kind of easy way to represent it, which I personally disagree, but well, it's actually.
Here's an explanation that made sense to me. Like, we're all used to, you take 2 apples and you put them together, or you take an apple here, you put them together, now you have 2. That's normal addition. What happens when you have 2 raindrops and you put them together? Does it create 2 raindrops? It creates 1 raindrop, right? And so that's not the normal math system. We could go and define a math system which says, when you add these 2 elements, it actually equals 1. And that would be useful because it would describe how raindrops had. You know, it just turns out that adding raindrops is not that useful, but it's a system that we could make. Similarly, there's some points here, and we're defining how they interact. And the way they interact is just, that's how they interact, that's what we say. Obviously, in the early days, people were trying to make a system, and they would maybe say, okay, well, you add this point to this point, and it equals this point. But then they kind of got stumped because they were like, oh, this isn't interesting. We can't find as many applications for this. We can't develop the theory further. So yeah, this is one of the hardest concepts to grasp. It's just, we're just defining things differently, and we're seeing what happens. Good question. Okay, so you might have thought, okay, so we can get 2 points and draw the line between them. But what happens when you try to add a point to itself? What if you try to do 4 plus 4? That's kind of weird because you have a point here, and now you're trying to draw a line between the same point, how does that work? Again, we just come in and say, this is how we're going to define it. We're going to define it to be the tangent line. The tangent line is the line you draw that is the same angle as where you are on the point. So if we chose this point here, the tangent line would be like this. If we chose it here, it would look like this. And we're going to see where that line intersects on the curve. And again, take the opposite point. Cool? Okay. We also call this point doubling because you're doing point plus point, or 2p, if your point is represented by the variable p. Cool, so we know how to add, and we know how to double a point. Cloudflare wrote this really good blog where they made some fancy GIFs, and it's just really nice to watch, and I think it helps you see in it dynamically what's going on. So what's happening here is they're adding a plus d, that equals e, or a plus b equals c, c plus a equals d, a plus d equals e. And it's just sort of jumping around. Okay? So that's the system. Yay. Okay. So here's where it gets very mathy. And I want to show this for people who are interested in it. And if you're not interested in it or it doesn't make sense, just don't worry about it. It's one of those things where it's like, okay, this is what you need to know to understand how to do it. But if you really want to know like the proofs of it and how it's working under the hood, this is the stuff you need to dig deeper into. Okay, so when we talk about elliptic curve cryptography and we talk about elliptic curves, we're not actually going to work with an elliptic curve per se, like this. It's smooth. We say it's defined over the reals. It's defined over the real numbers. It's continuous, like that. What we actually do is define it on a finite field, which is this mathematical entity of very general nature. Basically, you have a set of elements, and you have some operations defined on them, like addition, multiplication, and some nice properties fall out, like properties about those applications, which you can use to develop further theorems. Okay, so there's a finite number of elements. If we say defined over the reals, that actually means there's infinite values. But when we now have a finite, a non-infinite number of values, our elliptic curve changes into something like this: integer values, whole numbers, and their negatives. Okay? So you can kind of see it still has sort of the same structure because the points are symmetric around the x-axis. Right? You see these 2 points here, these 2 points here, and so on. So now we just define it for integer numbers between 0 and, or I guess whole numbers between 0 and some number n minus 1. N is just some big number. And the math still works the same. You still take 2 points. You don't really have the idea of like a slope anymore, which is why you need to go back to that algebraic equation way of looking at it to actually do the math. But the central idea is you're finding, you're taking 2 points and then finding where they intersect a third point. Or you're finding the tangent line and finding where it intersects a second point. Okay? How do people feel about this? People are quiet. And
So
it's hard to gauge.
It's like a finite translation of the continuous.
Yeah, it's taking infinite numbers and getting rid of, technically an infinite number of them, but getting rid of the ones that, for this application, we don't care about. And we're saying we only care about whole numbers.
So we just restricted something to whole numbers. Which variables were those?
The variables were the point on the curve.
The x coordinates.
So yeah, and the y coordinates as well. And the points, like, yeah, like this y value is a whole number.
Okay.
This y value is a whole number. Okay? And that's going to allow us to, that's going to give us some properties that we need to build a digital signature algorithm. Okay?
Yeah.
Cool.
I guess that implies that
Yeah.
the A and B are also have to be whole numbers, right?
Yes, yes, exactly. Yeah. These are just points, just like in high school math. You know, you have a curve and you have parentheses A comma B. They're just points. But they're integer points. I keep jumping back between integer and whole number because technically they're integers because you can get negative, like below the y-axis and to the left of the x-axis. But they can also be whole numbers, we'll see in a bit. So if that graphic is pleasing to you and this sort of thing interests you, I found this really good website online, which is also in the references, where you can build these finite fields on elliptic curves and do point addition and point multiplication. So you can define your curve parameters right here and put in different points, P and Q. See, a point P has an X value and a Y value, and then you can figure out what is the solution when you add them? What's the solution when you multiply them? So it's actually really cool. Some guy just made it because he was like me and was like, I don't understand this stuff. Let me try to build something so I understand it. So you can use that if you're interested in it. Okay, so let's keep going with finite fields. Why do we have finite fields? Well, first of all, what do we want out of a finite field? We want some addition and multiplication operation, which we already have on elliptic curves. We defined the point adding and point doubling. We have some finite set of elements. And the kinds of fields we're interested in are going to be of modulo sum prime. So what this means is we do some, like our addition and our multiplication, and then we take it modulo and a prime number. So here's the question. When I say modulo, who actually knows what that means? Okay. Another word for it is clock math or remainder math. And the idea is, think of a clock. And so actually, I'm from the US, so we wrap around, but I don't know how Canadians represent this, but when it's 1 in the afternoon, do you say it's 13 o'clock or 1 o'clock?
1 usually.
It's 1? Yeah. So you just did modular arithmetic. That is 1 mod 12. And what it's saying is, take your first number, like 11, or sorry, let's say 13. 13, divide it by 12, and then see what the remainder is. When you divide 13 by 12, 12 goes into 13 once, and then there's a remainder of 1. Similarly, if it's 3 o'clock in the afternoon, that's 15. 15 mod 12 is 3. And so they call it clock math because you can have a really large number, like 50 billion, but it will only ever be a number between 1 and 12 because you keep wrapping around the clock. Okay? So it turns out that doing this sort of, defining this sort of field leads to really interesting properties that allow you to do cool things like build digital signature algorithms. Okay? So we're going to define a field, and when we do the math, we're always going to take it mod some really large prime number. Prime number means it doesn't have any factors, and we also need that for interesting applications. So yeah?
I was just going to say you can often use the percent sign to do modular division in many languages.
Yeah.
And
So
it's
Python.
often useful.
Yeah. Yeah, Python and Node. Yeah.
Alex?
Yeah.
Why is 12 mod 12 12?
Yeah, so I had to make a decision there. I could have made 12 mod 12 0, but I wanted to keep in line with the clock math. So I just made it 12. Do you think it should be 0?
Well, it's mathematically have to be 0.
Well,
But for human beings, it would be noon. We would refer to it on the social layer as 12.
okay.
Like,
Thank you for
yeah, like
correcting.
You can say it as a point.
both are correct. Like the human layer would call it 12. The clock Yeah.
Cool.
If you're a computer.
Tell me further where.
How many people are computers?
Can you raise your hand a percentage? Like 70.
All right. So I probably should have defined that as 0, but whoops. So this is probably the worst we're going to get here math-wise. We want to define parameters on this elliptic curve defined over a finite field. And we want these parameters to be known because you need to know what these values are in order to actually do the digital signature algorithm. So we'll look at Bitcoin, what their parameters are in a bit. But the values you're interested in are that prime number p. That's what we're taking the modulo of, prime p. It's a prime number, has no factors. We're also looking at something called the order of the field. We represent that by capital N. And that's just the number of points in the field. So this is also a massively large number. And it's so large that you might be dismayed at first and think, oh, but how do we calculate what the number of points are in the field? It's going to be a huge number. It's going to be like to the 255 or something really large. So if we had to go through each one and calculate it, we would be here until the explosion of the sun. But someone named Schoof came up, a mathematician, cryptographer named Schoof, came up with an algorithm that can be run very quickly relative to the death of the sun and polynomial time. And it can find for us the number of points, so that value n. So that's really nice. Good, we can use it. Another value we want is little n, which is the order or the number of values in what's called a cyclic subgroup of the field. So it's a subgroup because here's our finite field, all the values, and we look at a subset of them. It's called cyclic because there's an operation you can perform that can generate each of the values in this subfield or in the subgroup, and then they wrap around and you generate them over, sort of like the clock math I mentioned before. So some things we need, we want this to be really large because the larger this is, the more points we can create, and thus the harder it is for someone to brute force and find one of our keys. These points are public and private keys. The points are public and private keys. So we want more points so we can create more keys and have it harder for someone to figure out what the keys are. We need this number to be prime, or else, well, having it be prime means that every value has an inverse. It means that you can take one number, find its inverse, or 1 point, find its inverse, multiply them together, and they equal 1. So in regular math world, 4, the inverse of 4 is 1 over 4. Because 4 times 1 over 4 is 1. Okay? So if we have a multiplicative inverse for every field in our cyclic subgroup, that means that we can perform our elliptic curve digital signature algorithm because we need to have an inverse. And we won't worry about Hass's theorem. So related to n, one more value is this. It's called a base point or a primitive element. This is pretty cool. There's an element in the cyclic subgroup which we can multiply by 1, 2, 3, 4, 5, and it will generate every value in the cyclic subgroup. So there's millions upon trillions of these values, and there's one number, when we multiply it, it will generate all of the values. And this is really useful because that's how we're going to generate our public keys. Okay, so this is just kind of definition, but these are the parameters that define an elliptic curve on a finite field. P is the prime, A and B were in the actual equation of the elliptic curve. N is the order of the subgroup. G is that base point that can generate n elements in the cyclic subgroup. And then H is this value, which is more interesting for cryptographers, and it's just a security parameter. And you want it to be low. You want it to be 1. So for Bitcoin, it's equal to 1. So, okay, thanks for getting me through that. That's going with me through that. That's the worst of the deep math we'll go into. Any questions on that? Anything I did wrong? Something I said wrong?
That is good.
wanted to ask a lot more questions, but I'll save them for after.
Fair enough. Okay. So let's get back to Bitcoin. I showed you these domain parameters and this elliptic curve because I want to bring it back to Bitcoin. I want to show you that this right here are the parameters for Bitcoin's elliptic curve. We call it it's called sec P256K1. Each of those letters means a certain thing, but what's interesting about it, I think, is so there's this group called NIST, and they're kind of a government group, kind of a like academic cryptography group, and they provide standards for what sort of curves we should use, which algorithms we should use, how we should generate cryptographically secure random numbers. And they didn't propose this curve. This was thought up and is more like proposed and backed up by the academic community. And some people like this because it's been shown that an algorithm which NIST put out might have had like secret backdoor parameters which the NSA could take advantage of to break this particular type of cryptography. And we want something that is going to work for everyone. So people don't really trust, some people don't really trust NIST anymore. So it's good to see a curve which isn't put out by NIST. I forget what NIST stands for, but it's some...
National Institute of Standards and Testing, I think.
Thank you. Yeah. Okay. So take a break after that. Any questions? What I wanted to talk about there was just show you what elliptic curves are, how you add them, how you multiply points, and some of the parameters that we use to define them.
Yeah. So that all sounds really arbitrary.
Yeah.
So, I mean, is there like a mathematical perspective from which that falls out more naturally, and someone saw that and said, hey, it'd be useful? Or is it really like this? Is it really as arbitrary as it looks like it's the result of desperate search for anything that would work?
That's a really good question, and I don't know. Because for me, it's kind of been a desperate search of looking and picking up pieces. What do you think?
Yes, there is a... So basically, elliptical curve, like how it works when Alex showed what like you just took 2 points and make some intersections, looks like weird. What the fuck on earth you want to do some kind of line and some curve? It sounds very unnatural. However, it's all based on a simple fact, on a simple math, which was like invented like many years ago, but as a cryptography it was proposed in the 70s. When you have 2 large prime numbers and you multiply them, it's very difficult without knowing those prime numbers to factorize them. So I have one prime number, I have another prime number, I multiply them, and only me, I know how I create this number. If I give you this, like, how do you call it, multiplication to Alex, he wouldn't able to find how did I, what were those numbers.
But you're talking about a different system.
No, really. It's actually the same. It's the same basics. So instead of multiplication on natural numbers, which can be like from 1 up to infinity, you just say, okay, let's just do some numbers up to some point. We're just gonna take some big prime number and gonna use this modular stuff.
Yeah.
So you create a sort of group. So every number you have on this modular stuff, you can multiply these numbers, you can add those numbers, but those numbers gonna be from 0 up to this prime number -1. And this elliptic curve, it's more generalization. We say, okay, so let's just do not on this, it's called a Billion group, but in our one, we're gonna use instead of prime numbers, we're gonna use some point, discrete point on this curve. This curve doesn't really matter. I mean, it's just more like, it looks curve if you do not use prime numbers. It's just like you use some kind of way to show it up easily. Graphical representation, what it feels somehow more natural. But through it, you have some equation, and solution of those equations also formulate this kind of group. When you can add it to numbers, and the addition of those 2 numbers is going to be also solution of this equation. So you have the same principle. And then you create this group. It works absolutely the same as before. You have 2 numbers, you multiply them, it's very difficult to find divisor. It's exactly how it works.
So I guess what I'm wondering is, this group that we're using, that's created by bouncing around an elliptic curve.
Yeah.
Like, were people doing that before they were using it for crypto, or was it invented just for that?
It wasn't like it's mathematical group. It was invented just for sake of invention as a whole math. So it just was like very good example. It's very, very difficult to reverse this operation.
I think that's the most important part is like the math has been there for a while, but suddenly this application of, hey, if we have a problem which is hard to do one way but easy to do the other way, we can use that to create a crypto system. It's like, I don't know, like people were always boiling water, right? But then they figured out if we boil the water and compress it, we can create a steam engine, and that's useful.
Right. So previously there have been people staring at their favorite equation and writing papers about, oh, there's a pattern here.
For hundreds
Their
of years.
favorite equation.
There's a cool pattern here.
As is tradition.
You don't notice me until we need it.
Yeah,
A
for
lot
us,
of math was just like, I don't know, basically like aristocrats and wealthy people just finding interesting things out about the world.
well, I'm an example of guy. I have math education. It's exactly what did I do in university. So there is one book about one also similar group. You just added numbers and it became number also in this group, and you make a different theorems, different lemmas, and a whole big book about 1,000 pages. At the end of the last pages, you prove what this group doesn't exist. So people were just creating this book like significant amount of time to prove what it cannot exist actually. Like never.
Seems like really good, well-rounded practice in these matters.
Yeah,
to be like, okay, now.
Creating all those kind of groups, classify them, and it's a book about like 5 tomes. So just to make a classification of these groups, just to explore all possibilities without any application whatsoever.
But as you pointed out earlier, we don't have proof that these hard problems are sort of hard because of anything that comes from mathematical first principles. So
Yes.
the choice of prime factorization or elliptic curve math doesn't come from some general theory
Yes.
of how cryptography must be. They were sort of pre-existent difficult problems where the difficulty went from being a problem to being a solution.
That's a good way to put it.
Cryptography was discovered.
Yep. Another thing about the finite fields is that imagine, so all we're doing is taking a point and raising it to some power. If you just do that with regular numbers, like 4 raised to the power of 1,000, you can just take the 1,000, you get that some large number, right? Let's just call it n. It's really quick to take the 1,000th root of that number and find your original number that you multiplied by. But when we have the finite field where it's zipping around and jumping and it loses itself in that rotation about the clock, it's not easy to take the number and just divide it. There's not an equivalent idea of division. It's multiplication by the multiplicative inverse. Like just like taking 4 and multiplying by 1 over 4 is, you can divide that way. Sort of similar in finite fields. So we don't have this idea of division, which is really good for our use case because we don't want it to be easy to find what that product came from.
Yeah, can you give more, like, kind of related to that, can you give more of like the social layer level of why this is so trustworthy? You know, like, because I'm a fan of the code is law, mathematics sort of core. And so essentially, I tend to look at things like that. Like, I like crypto for its game theory proof elements. So mathematically, like, this is really, really, really hard math for a computer, much less a human being, to do. Is there something that particularly protects it ideologically, like that makes it fraud proof or whatever? Why is this the cryptography that is being employed primarily?
Because of that discrete logarithm problem.
Okay, that we don't even know if we can solve. Like that. Yeah. Okay. Yeah. Unproven.
So that's why it's the most amazing thing to me is like, you go down and there's really no basis for it. It's just we haven't found the solution.
Mm-hmm.
So it's on faith.
Not really. It's almost like proof of work because if it's being uncracked, like this is how, like, sort of how you measure how good cryptography is, right? It's like
okay, everybody's been trying to crack this for how many years? Nobody's done it. That makes it safer than something that just invented 2 years ago, right?
Yeah, I mean, it seems like the majority of cryptography is like that. Obviously, it relies on some, like, obviously a lot of math to prove to people, to academics, to engineers that it works. But when you go down and like stare on the very core parts of it, yeah, we don't have a proof that like proof of work uses SHA-256, it's a hashing algorithm. We don't have proof that this is unbreakable. Sort of related, going back to the quantum stuff, we actually do have a proof that a quantum method of encryption is the best we can do. And that is maybe because it relies on a totally different set of mathematics, quantum mechanics, rather than this cryptography, classical cryptography it's called, which we've been working with. But yeah, for the most part, it's reliant on, I don't know if I call it faith, because faith makes it seem like it's like striving for something. It's more like faith that it won't be broken, I guess. I don't know.
Faith.
It's
I just think it's fun. I just think it's kind of ironic and funny.
It is.
Think of it that way.
Mm-hmm.
Yeah, it's ironic and funny that all of this system is at its core unproven that it works. But it does work, and we'll use it until it does.
Compare it to a one-dimensional block, you'd be fairly confident that no one's going to come around and lift it with their bare hands. Maybe someone will hold a tractor.
Exactly.
So you're saying there's a chance?
Yes. Oh, yeah.
Cameron.
Almost certainly these will all be broken. Yeah. Given enough time and clever humans, yeah.
Motivation.
Yeah. Yeah, so you can think of Bitcoin as a like $10 billion incentive to find the solution, fast solution to the DLP problem. So you could make a lot of money. Okay, so we talked about elliptic curves. Now we're going to take it back to, or actually introduce and look at this digital signature algorithm I've been mentioning and talking about. So remember public-private key cryptography. We have these two keys, public and private key. They're really large numbers, and we need to generate them, and we can use our curve to generate them. Okay? And just an aside, for folks who know what RSA is, RSA signatures, the reason we like this algorithm, in some cases, better than RSA, is that over time, the mathematical community has found ways of decreasing the security of RSA faster than the elliptic curve digital signature algorithm. So how this manifests itself is that you need a much, much larger key to have it be the same difficulty to crack as a smaller EC key, elliptic curve key. So one comparison I found was that a 256-bit elliptic curve key has the same security. It would require the same roughly amount of computation as a 3,000-bit RSA key. Okay, so it's more than 10 times as large number of bits. And also elliptic curves, because elliptic curve cryptography, because of the smaller keys, it's faster. You can create signatures faster. So here's just one data point from Cloudflare where they were able to create signatures roughly 10 times faster. So we're going away from the more like abstract theoretical parts and getting now more into the application engineering. How do we use this? Okay, so how do we generate our private key? Remember, we have those domain parameters. We have the base point. We have the curve parameters. All we do is we pick a random number between 1 and n, where n was the size of that subgroup. And that's our private key. It's just a random number. And we have good methods for generating random numbers very quickly. So this is very fast to do. And then to create our public key, this is the one that we share with everyone, we're going to take that base point g and multiply it by our random number, our private key. Okay? So this, going back, this was why it was really important to have a subgroup size that's really large. Is the larger subgroup we have, the more values we can create by multiplying our random private key by the base point. By G. G is the base point. G is a point which is, you can multiply it by a bunch of numbers, and it will generate every element within the set. So yeah, this is confusing. This took me a while to understand. There's the finite field, which is like all these elements. We find a subgroup that's of prime size, prime number size, and then we have a base point which can jump around the curve and generate every single point within that subgroup. More points, more security.
Sort of like addition. You add one, so one would be base.
Exactly.
For addition.
Yeah, that's one way to look at it. Yeah, it's a good analogy.
So
Okay.
is G, for Bitcoin, G is a fixed, maybe you showed it on an earlier slide, did you? It's like a
Yep.
fixed number that everyone knows, is that?
Yep. So baked into the Bitcoin D software, also Ethereum, because they use SEC-P56K1, also Zcash, all these guys are these parameters. Also in OpenSSL, which is a super well-known, well-used cryptographic library, these values are in there. Yep.
And where's the random number generated from? Is it in the code somehow? Or?
It is code that generates it, but it's just like you have entropy in your machine. You have randomness in your machine that it collects from like reading random disk accesses and sort of environment information. And then it uses that as a seed. It seeds the random number generator. And then we have algorithms for generating random numbers. And they're called pseudo-random because technically they're generated by like a known process. There's this idea of randomness, which is like the weather patterns forming and like do you know what Brownian motion is? Brownian motion is random, it's just the movement of atoms. And then there's this idea of pseudo-random, which is where like we have an algorithm which generates numbers which look random, but if you know the seed, you can generate all of them. So that's how we generate random numbers, usually. Okay. So, wait. Cool. So what we're doing here is we're trying to sign messages. We take a message, M, we take our private key, and we now take another random number, K. Okay, we take a random number, K, and we perform this elliptic curve digital signature algorithm, and out pops our signature. Okay, so 3 inputs. The message we want to sign, our private key, and this random number, K, which is between 1 and N. And that creates this the signature, which is really like 2 values, R and S. So if Alice wants to go and send her invoice, going way back to the original Alice and Bob example. So this is the algorithm. If anyone wants, we can go through it, but it's not really interesting to go through. The important parts to remember are the random K value, the private key, and you take your message and you actually hash it. So if you're familiar with proof of work, hashing is taking some input value and then mapping it to some random string of bits. We hash it. We hash the message that we want to sign. And then we sign that hash. So now on the other side, Bob takes the message, the public key, takes the public key of Alice and the signature, and he runs it through an algorithm which pops out either true or false. True if it's a valid signature, false if it's not. Okay? And this is the algorithm for doing the signature verification. And pretty much he's just comparing the result of this computation to the signature that Alice gave him. And if they're not equal, it throws a red flag. And if they're equal, life is good.
Question.
Yep.
What's the reason for bringing K into the picture? Like what? You don't need to know K to verify the signature.
Right.
So
right.
like what?
I don't know the real reason. My thought would be that you need some sort of randomness in the signature in order to like distinguish different messages. So imagine like it's really common, for instance, for like think of a website like Google. Google, think of every time someone says like cat photos in, right? You want a random number so that me looking up cat photos and sending the message in is different from you looking up cat photos and sending the message in.
So I mean, so if I sign the same message twice, I'm going to get two different signatures.
If you use a different K?
Yeah, I mean,
yes.
like just conventionally using tools, if I open up GPG and sign something twice, am I going to get two different outputs?
Yeah, if you sign the same message with two different Ks.
And you're using the same K more than once is really, really bad.
Yes, so we will look at that.
Okay, sorry.
Yeah. No, it's good. You're anticipating it.
Is that like the idea of nonce?
Kind of, except a nonce is not random. Or it doesn't have to be random. Like a nonce in proof of work, it can really just be 0, 1, 2, 3, 4, 5. But it is similar like a nonce in that for one, like a nonce that's just a little bit different between like 1 and 2, it will generate a totally different output value. All good? Yes, thank you for asking questions. It makes life so much better. Thank you. Okay. Cool, so I want to bring this back to Bitcoin more. I gave this example of Alice sending the invoice to Bob as how you would use these digital signatures. But they're used kind of in the algorithm is the same, but they're used a little differently in Bitcoin. Instead of sending to a single person like in this example between Alice and Bob, in Bitcoin, what you're doing is you're using the elliptic curve digital signature algorithm to say the owner of this public key attests and agrees to send 5 Bitcoin to this address. Okay, and the address is actually just another public key. It's like a hashed version of the public key, but it's a public key. And the whole reason the system works is that the only way that Alice could create that signature, that message, and then create the signature for it, is because she has the private key. If we didn't have a secure digital signature algorithm, if it was possible for me to come in and create a message and convince everyone that I, in fact, said, yeah, it's okay to send this 5 BTC of Alice's to me, that would be a horrible system, right? The money would not be protected. So that's how digital signatures are used in Bitcoin. We use the relationship between the public and private key to tell the network, now 1NF6 ... is the owner of these keys, or is the owner of these Bitcoin. And the reason they're the owner of the Bitcoin is presumably they have the private key for that address. They have the private key for that address, and they can send it. Okay, so we're almost done. I want to talk about 2 sort of now applications of this algorithm, or interesting points of this algorithm. So one is what you brought up, is if you reuse the K values, those random K values in the signature creation algorithm, so that random K, this is when we're creating a signature, if you reuse that, then someone can find your private key. And this happened in 2013 in a Java program for the Android Bitcoin wallet. Android's written in Java. It used this library called Bouncy, or it used this class called Secure Random, that the owner of this Android wallet was like, this is trash. Like, this is not generating secured signatures, because it wasn't generating completely random K values. There was some relationship between successive K values that the software created. And so an attacker, once they figured out this relationship, would know the different Ks. And then it's just a system of equations where you can solve for the private key. So a bunch of Bitcoin were lost this way. And this is how, like, you can say the math works perfectly, but there's really subtle problems that attackers immediately take advantage of. and screw you over. So it's a scary world.
Do my eyes betray me, or is that an op-ed by Vitalik from 2013?
That's the other cool thing is way back in the day
community
when
warrior.
Vitalik was not like a billion-dollar Ethereum guy. He was writing for Bitcoin Magazine.
Aww. Protecting people from vulnerabilities to the best of his ability.
I'm just curious, does that have anything to do with replay attacks? Like when there's a fork and you send your coins after the fork.
Yeah.
I heard that if someone gets the transaction ID, they can figure out.
No, the replay attack is like there's two networks, and one of the networks creates a transaction, broadcasts it. But since that transaction is valid on both networks, even if the person just wanted to send some BTC, like from wallet A or address A to address B, the other network, BCH, Bitcoin Cash, will also see that transaction. It's valid. They'll broadcast it to everyone, and then those funds on the Bitcoin Cash network will also be sent.
But whoa, though. Bitcoin Cash built in replay protection, though, right? It was, we were worried that 2x wasn't going to.
Sorry, I misspoke.
No. Yeah. Because that's the only reason we didn't get shook up with the altcoin known as Bitcoin Cash. Is just like they didn't try to. I feel like the main problem of a replay attack is mostly just the conundrums it would cause. Like it's mostly just. It's again a human layer error of like, oh no, which of these chains are we transacting on? Yeah.
Because they move together.
People can fork Bitcoin all they want and call it Bitcoin insert word here, as long as they don't make it so that those transactions can be claimed against the Bitcoin core fork. Like I feel replay attacks. That's one of the things that's been most worrying to me. Indirectly in the tumultuous drama of Bitcoin 2017. It's like, cool, okay, people are buying, they're selling, whatever. But any sort of thing where you're going to fork, but then also not build in protections to designate that you're running a completely different timeline here. You're running a different, I don't know.
They wanted to be the real Bitcoin, so they figured, the real Bitcoin shouldn't have to write replay protection because we're the real one.
Oh my God. It's like pop culture. It's insane.
About that? Okay. Yeah, so key point here, you have to generate cryptographically secure random. So if they're related, that's not cryptographically secure. And then you get home.
When you say related, what do you mean by that?
I mean that given two random values, K1 and K2, knowing K1, you can infer what K2 will be. And usually that's not random. That's like saying, given one coin flip, I would know what the next one would be. Because coin flips are random. Okay, so the last thing I want to talk about is transaction malleability and SegWit. So
sorry, man.
Of course, yeah.
All you can, I don't understand it either, but does it get broadcast with the message? Or is it kept private
It's kept private. Yeah.
So then how can the public key verify without knowing the value of K?
We'd have to go back and just look at this algorithm and try to figure out why K wasn't needed. But K is not there, so pretty sure it wasn't needed.
But it gets worked in the signature, doesn't it? So you don't need it at this stage. It's sort of consumed by the function that initially produces the signature. I don't know.
Maybe. Yeah, I don't think we know.
Okay. Or Bell is working.
Yeah. Yay, it's fixed. By God himself. We don't have to touch it.
Okay. Who here actually understands what SegWit was for? Who was SegWit for?
What SegWit was intending to accomplish?
What?
Yeah.
What was the most important thing about SegWit?
It was to destroy Satoshi's vision.
Yes, right. It was to make Bitcoin maximalist correct. No, it was to.
Yeah.
Yes.
People get so worked up over the 2 megabytes of like, well, we got to scale Bitcoin. SegWit is too complicated. SegWit doesn't do 2 megablocks. Not the true vision. SegWit was just about fixing transaction malleability. And then they figured out that actually they can soft fork in a increase in the blockchain like virtual size, which is what they did just to make it more palatable. Easier for the RDTC folk to swallow, but that did not work out at all. So what is transaction malleability? Transaction malleability is where when you have a transaction, it's just a blob of data, right? At a high level, it's signature data, like what we just looked at with the ECDSA, and then it's data that tells what the transaction's doing. It's sending these, from these addresses, it's sending 5 Bitcoin to these addresses, okay? And we create an identifier. Every transaction has an identifier, TX ID. And the way it does that is it takes the whole blob of data and hashes it. So hashing is where you have some input data and it maps it, it sends it like a function, to some random collection of bits. Okay? It's the same hashing that's done in proof of work, SHA-256. So the thing with hashes is that if you change 1 bit in the input data, the output data is going to be totally different. Okay? So if you can change your input data, but still have it be valid, you can create 2 versions of the same transaction that have totally separate IDs. And this is a problem if you're trying to build something like Lightning Network or cross-chain atomic swaps, because you need to chain transactions together. That's how SegWit, or that's how Lightning works, is chaining a bunch of transactions that reference previous ones. And if suddenly this transaction, for instance, references TXA, and then suddenly TXA is TXZ, something totally different, the process doesn't work. So, what is this related to signatures? Back in 2012, this guy, Serio Damon Lerner, figured out the way ECDSA works is that you can change a couple bits and still have a valid signature because of how that finite field mathematics work. So he pointed out that, remember the signature was R and S? We created these values here, R and S. That's the signature we created. Turns out that if you take negative S mod n, which is the size of the subgroup, that's also a valid signature. And the way to think about it is that, go back to the curve. If you have some points like R and S, R and negative S are also valid. Negative S are also valid. So this is a problem because negative S is different from S. It's a bit flip, maybe a couple bit flips. I'm not sure how it's represented. And that's going to create a different hash. So how did SegWit solve this? Remember I said earlier how there's sort of 2 levels to the transaction. There's what the transaction does, and then the signature, also called a witness. Segregated witness teased those apart. Where before, the data that was hashed used to be both the signature data and the data describing what the transaction does. Now, the data that's hashed is only telling what the transaction does. Who it's sending from, who it's sending to, how much. And that other data, the signature data, the witness data, is segregated. It's pushed off to the side. It's no longer part of the hash. And all of the software now that is SegWit compatible, it still needs the signature data. It needs to verify that it's valid. But it's no longer in the hashed portion of the transaction. So there's actually like 5 or 6 ways you can do transaction malleability, but this is the one that's directly related to how ECDSA works, and just the underlying math of it, which you now understand because you've seen how how elliptic curves add, and how those values are symmetric across the x-axis. S, negative S.
The thing I'm still confused about is, and I'm probably thinking about it wrong, once the transaction is in blockchain,
Yeah.
you know, they say it's immutable. So how, like, how do you trick it into, you know what I mean?
Thanks for asking that. Very good question. I skipped over that. So you're right. Once it's in the chain, it's solid. It's in there. But what happens when it's unconfirmed? Think of the network of Bitcoin nodes, and it's just a bunch of computers. And like in my mind, when I think of a transaction spreading, it's broadcasted by some node in Slovakia, and then it spreads like a wave through the world. What happens when you have chain analysis, a company that that has nodes all over the world with extremely fast connections? What happens when one of its nodes figures out that there's a transaction here? It very quickly sends the information over to US and then starts sending out a validated transaction.
Oh, okay.
So now you have like two views of the unconfirmed chain. You have the Slovakia-based one, which thinks that TXA is the valid ID. And then you have the US one, which thinks TXB is the valid one. So...
But does that get resolved?
Yeah, so how does it get resolved? How does any blockchain get resolved? It gets mined.
Right,
So whichever transaction gets included in the chain, the other one will be marked as invalid.
So we're worried about the malleability before it gets
Exactly.
in? Okay.
Yeah.
Well, malleability made watching for transactions much more computational because you have to go through every transaction and look at all the details to actually see if that's the transaction you care about. But if it's not malleable, then you can just look at the IDs. So it saves you a lot of time.
Okay.
Yeah, I can tell you that in our company we called it a normalized TXID, and it doesn't include data about the signature. So we kind of like home rolled, and other companies do this. We kind of made our own TX hash algorithm, which would uniquely identify transactions. So we'd see two transactions that would have the same normalized ID, but would have different blockchain IDs because they've been validated by the network. Yeah.
Still don't get what's the problem here.
Yeah.
So I can, for example, I have a wallet, I have 1 Bitcoin. I send
Yeah.
you like 0.9 Bitcoins, like 0.14 fee. So somebody saying, aha, so there is like a transaction with this particular signature. And they can flip this signature for a different one.
Yes.
However, it will be still same transaction.
No, it won't. It'll be a different ID. Because, like...
It'll be moving the same funds.
Yeah. Yeah. Sorry. Yeah. What do you mean by same transaction?
Like, what exactly an issue?
What would be I think I'm on the same page, maybe what would be accomplished by the fraud that this is preventing? If it is ultimately Okay.
General annoyance. So like...
Annoyance?
Annoyance, like people just wanting to be assholes and screw with the system.
Because I didn't know
because it screws with the system because you, for instance, like we're affected by this. So I'll give you an example from my life. I'm sitting there and then I get a bug report which says, hey, we broadcasted these transactions, but they're not showing up on the chain. What happened? And then, actually, it's even worse. So people will send one transaction, then send another transaction which uses the first transaction's outputs to create the second transaction. And they'll create these chains of unconfirmed transactions. When that first transaction gets validated, all the following transactions are now actually invalid. Because they reference by TXID that first transaction.
How is it different if I broadcast two transactions? I just spent 0.9 and from same wallet I sent second invalid transaction because of double spending.
It's not about double spending.
It will be same transaction, I will say same amount of funds, but just different letter after like 10 digits after the comma, but it will have a different signature.
Yeah,
How's
and
it
a different
different?
TXID.
Yes.
Right.
I knew about the structure of SegWit, but I always thought that it was solely addressing trying to speed up, like trying to address the scaling problem and trying to, like, I didn't realize that there was a genuine area for potentially malicious activity there. That it was, I thought it was just, okay, if we separate out the signatures as a separate batch of information, like almost kind of like a pre-processing for Lightning of like, okay, this will be easier to parse if we have the signatures separated out as a separate batch of data. So yeah, no, thank you. I didn't know any of that.
But I want to answer your question because you look confused and
I'm
yeah.
still.
So I need to draw something.
I can give you really an example. Is let's just say you're a company, you're accepting unconfirmed transactions. So I get the transaction once, I credit you for like 1 Bitcoin that you just sent me. It gets malleated, so I credit you twice. Now I'm like crediting you twice for 2 transactions, and I'm waiting for them to get confirmed. One of them gets confirmed, the other one doesn't. I'm like, well, do I take away that 1 coin from you? You know, as a business, I can correct for that, but it's a giant pain, and most businesses probably don't.
Okay, look it up. So probably something, or I misunderstood something, or it's something which is very weird.
Well, that's a programming thing. The other thing is, if you have like a Lightning Network transaction or something like that, you're building all these transactions on top of each other. If the base of all that gets changed to a different hash, then all those Lightning transactions just die. So you,
So it sounds like an efficiency issue.
Yeah. So, do
Maybe.
people want me to go through this? Yeah.
Do it.
So, here's me, and I generate this transaction TX1. Really, it's like a long string of random numbers, but we'll just call it TX1. It's unconfirmed. Actually, I'll just mark it as it's unconfirmed. And it has like output 1 and output 1 and output 2. And then I create another transaction, which is also unconfirmed, which spends those inputs, and it's TX2. Right? And let's say I'm in exchange, so I see these funds, and I credited a real person in meat space with fiat currency. Right? I gave, based on sending these transactions, within my database, I gave the recipients of this transaction, so this is out 3 and out 4, I gave them $20,000, because that was the value of the transaction. And you know, I expect Bitcoin to work. If I send out the transaction, it's valid, it should work. But now, this guy on the other side of the world gets my transaction, malleates it to be TXZ by changing the signature. He broadcasts it to the world, and then that one gets mined. Okay, that one gets included in the blockchain, it's forever in the blockchain. Now, all of the other nodes which find this transaction mark it as invalid, because it's referencing a different transaction than the one that they see in the chain. They think that it's double spending. So someone mentioned double spending before. I guess it is actually related to that. But the problem is this way of referencing previous transactions. They're referenced by the TX ID. And when you change it to TXZ, suddenly TX2 is no longer valid.
So, bigger picture, harm done at the end is what? Like,
say that again.
So what's the real, like the harm done in the real world at the end of this when that happens?
It's pretty small.
Well,
trying to minimize the attacks there
no,
as
no,
possible.
it can be really big. So there's kind of two things I see that's bad. One is just the like day-to-day problems. Like that person who got sent the $20,000, that's no longer valid. That's not in the chain. That second transaction never gets in the chain. So the person who was meant to receive those funds receives them.
So we're discussing things that happen before the transaction is confirmed, right? Like if someone's expecting their transaction to be confirmed, it's taking
Yes.
So there's like, it makes.
So they could just wait. You're saying why don't they wait?
I mean, I'm speaking as someone who has has hardly used Bitcoin, right? I read about it when it first hit the news, and one of the pieces I remember was that there is this phenomenon of having to wait for your transactions to be confirmed.
Yes.
And I guess it surprises me to hear it suggested that someone would not.
They do. We have chains, so Bitcoin D, I think, does not allow chains of unconfirmed transactions greater than like 250. But we see those very often at my company. Exchanges that just want to send and send. And it's like a security parameter. The more you wait, the more secure it is. The less likely it's going to get flipped out.
Yeah, a lot of times you want to send faster than the block times are coming.
Yeah.
But your outputs are all, like, oftentimes you have to spend large outputs in order to
fund your wallet. You need unspent.
well, yeah, like, exactly. Like you have to use these large outputs that you want to spend.
And it's hard to explain that because like unspents are this low-level idea, which I'm not. Are you familiar with unspents? Yeah.
Peripherally.
Yeah. It's. Yeah.
So Alex, I haven't butted in till this point because this has been fucking delightful straight up. We're at double time. We're at 90 minutes. And mainly my phone battery's going to die and I don't want to miss the end of the actual presentation. I think we will all be down to nerd out further after it, but oh, dope. Nice.
Yeah, this is just my last slide.
Wrap up slide.
But,
okay. I want to get it on.
These are other
on
interesting things that I didn't have time. didn't talk about, but some things are like, how do you actually break ECDSA? What are the algorithms that try to find that private key and solve the discrete logarithm problem? Maybe you've heard about Schnorr signatures, which are a type of signature on elliptic curves, which allows you to do, they're really simple, and they allow you to do interesting things like aggregating signatures into one block. So this is an interesting thing because like my company has really large transactions because we're multi-sig. But if we could collapse 3 signatures into one, that would save a lot of space because signatures are the most meaty part of the transaction. Looking at other curves besides Sec P256K1, so twisted Edwards curves are another type of elliptic curve that people have created cryptographic schemes for. We spoke a little bit about quantum computing, but DLP can break because of that. And then just like an aside, this is making me realize you just need to look at code to really understand it. And so there's an NPM JavaScript package called Elliptic in NPM, and if anyone wants to read that with me, we can do that, because I want to understand it more. We can do it now. Yeah, afterwards, after the key signing party. Okay, so these are all the references. This has been really fun. I hope it was fun for you, but I really like sharing this stuff, and it's just so cool and really powerful. So, yeah, thanks for coming.
Thank you.